Hi, I'm David Romps, and I'm going to try to make the case that we should spend more effort trying to understand the planet at very high CO2 concentrations and very high temperatures. So the title of my talk, if I can put myself in the corner here, is the ECS Bump. If you push the planet out to very high temperatures, there's growing evidence that ECS, the equilibrium climate sensitivity, is not constant, but actually increases and experiences a peak out at high temperatures. So I want to really begin here by thinking about the Eocene. So the Eocene is a time where you've got guys with great big horns over here, and you've got birds eating mammals over here, but so lots of weird stuff, to us at least. But what's important for the purposes of this talk is that the Eocene is very hot, as you know. If we look at the temperatures over the Phanerozoic, with current day over on the right, and we go back in time, then the Eocene, some 50 million years ago, is one of the hottest times during the Phanerozoic, with temperatures some maybe 14 Kelvin above pre-industrial. If you want to find temperatures or climates that are warmer than that during the Phanerozoic, you have to leave our home of Earth and go to Venus. And on Venus, things are so hot that, of course, lead melts down at the surface. So Venus has gone through a runaway where it was unable to shed heat by increasing its temperature, so it just ramped up in temperature until finally it could shove radiation out a different window. And it's locked now in this runaway state. Now, common wisdom is that we cannot push Earth to a runaway state by burning fossil fuels, but we should probably make sure that we understand that really quite well. And we should also understand if there are any other surprises waiting for us at very high CO2 or very high temperatures, because it doesn't take a full runaway to kind of ruin your day. And so some of the evidence that's began to accumulate over the past 10 years, it comes from a variety of papers, and I'll touch on just a few of them here. The first is this paper by LeConte et al. In 2013, where they showed that as you increase the solar flux, the response of the planet is not just linear. As you get out to higher solar flux and higher temperatures, the planet starts to warm more for each increment of additional solar flux. So the sensitivity of the planet increases. So that's an indication that something nonlinear is going on at these warm temperatures. A couple years later, Wolf and Toon had this paper where they looked at 3 different climate models and probed that increase in climate sensitivity. In fact, they probed it so well that they found it was a bump. They went up one side and back down the other, showing that at high temperatures, maybe, starting around 300, 310 Kelvin or so, you start to have this growth, this peak, this bump in equilibrium climate sensitivity. A year later, Max Popp and colleagues tried to probe this in more detail, and what they're showing here are time series. So the x-axis is time, and the y-axis is the global mean temperature, and each different colored curve is a different GCM simulation. One would say a different solar flux or a different CO2 concentration. And what they find is that they can't quite seem to get a GCM to settle down, to equilibrate with a global mean temperature between 300 and 330 Kelvin. So if they try to just inch up the CO2 to just slightly push the GCM up into that gray region, as soon as it gets there, it says, I don't want to be here, and it flies off to above 330 Kelvin. So that means potentially that what we're talking about here is not just an ECS bump, but an infinite ECS. And if it takes only an infinitesimal increase in CO2 to give you a 30 K increase in mean temperature, then that's effectively an infinite ECS. So, okay, so we're seeing nonlinearity, we're seeing bumps, we're seeing this potentially infinite ECS. That's a lot of weird stuff going on at high temperatures. Now, I want to make the point about some context here. So here I've scaled down that plot and made so we can see a larger range of temperature. So going up to 800 Kelvin here. So if we look at Venus, a full Venusian runaway is all the way up here at 700 some Kelvin. And what's happening in the simulations down here is really at a much smaller temperature range. So maybe we could call this a terrestrial mini runaway. It's not a full runaway, but it's certainly something weird going on, and by weird I mean also bad, in that it would push the planet to very warm temperatures. Right? We shouldn't take solace in the fact that we wouldn't melt lead. If you actually go up to these temperatures, they would be lethal. And by lethal, I mean that if you try to go outside, you would perish in a matter of minutes. And to those of you who say, well, I go into a sauna, and the sauna's temperatures is at least this high, so this can't be that bad, I'll remind you that the relative humidity in a sauna is low, measured in typically single digits of percent. Whereas here, we'd have typical terrestrial relative humidities, and it would be absolutely lethal. So this is not a good climate. This is not one we want to ever push towards. So, do we have to worry about this? And the answer is maybe yes. Because if we go back to the Eocene, what was the temperature of the Eocene? It was global mean temperature just above 300 Kelvin, maybe sitting right around here, just inside this gray zone. And so today the continents are in different places, we have different vegetation, but are we so confident that we could push ourselves to an Eocene climate and not fall off the precipice? I think that's a really important question for us to answer. Like I said, we definitely have the fossil fuels to go there, the 5 teratons of fossil fuel plus however many teratons of methane clathrates might get released. We could almost certainly push ourselves back to this kind of Eocene climate. So we should know what the planet might do in response to that human behavior. So if we look at these 3 different studies and just kind of vertically align them on a temperature axis, we see they're all doing funny stuff and around the same place, maybe 300 to 320 Kelvin. And so there are some questions we might want to answer about this. What role do clouds play in this bump? Are they an essential piece, or are they just slight modifiers of what's going on? What does this bump really look like? If you look at the middle one here, there are 2 simulations that are spanning 25 Kelvin. Well, if this bump is really there, we want to know, one, is it infinite? And if it's not, what does it look like? We want to probe it at much finer temperature increments. So to get at those types of questions, I wrote this paper, which I feel like I wrote ages ago, well before the pandemic, but it just came out a couple months ago. And what it does is it explores this ECS bump in a cloud resolving model to see what maybe role clouds play, and to really sample that bump in really high detail. Now, to do that, I have to stray a bit from the standard methodology. The standard methodology is you set the CO2 concentration and you let the SST equilibrate to that. And that's a fine way of doing things. The problem is it's very slow. So alternatively, what I've done here is something different. I've fixed the SST and let the CO2 evolve prognostically. So I give the CO2 an equation, a prognostic equation that is going to asymptote to a value that would close the top of atmosphere energy budget. And it's not obvious a priori that that would be faster, but if you work through the math and then actually try it, you see that it is. It's about 30 times faster to get to equilibration than the standard slab ocean technique. Or another way of phrasing that is you buy one and get 29 free. And if you're trying to probe temperature over really fine gradations, then you could really use those 29 free simulations. So that's the technique that I use in this paper. And then you crank up a whole bunch of cloud resolving models, set the SSTs in 1 Kelvin increments, solve for the CO2, let everything equilibrate, and then you can read off what the forcing is as a function of SST and also the climate sensitivity. So when we do that, what we see is that the forcing increases monotonically as a function of global mean temperature, and the climate sensitivity has this bump in it. It's not as big a bump as you get in the GCMs, but it's there, and look, it's in the same place, around 310 Kelvin or so. If you multiply those two together, you get the ECS, the equilibrium climate sensitivity, which has this rising behavior and that bump. Okay, and we also see, because we've probed this at really fine temperature gradations, that there's no infinite ECS, at least not in this limited area RCE cloud resolving model kind of setup. If there is an infinite ECS behavior in a GCM, it is likely due to some aspect of the large-scale circulations, interactions with maybe clouds. So something we need to understand. So what we get out of this is we learn that it's a clear sky phenomenon. I didn't show that in the paper, but if you take away the clouds, you get basically, qualitatively the same thing. And we can also show that it's not just an artifact of the radiation scheme, which is something I worried about in the beginning. If you rerun the cloud resolving model with line-by-line radiation code, you get qualitatively the same thing. Okay, so this gives you a hint that maybe you don't need a cloud resolving model if clouds aren't that important, at least for the kind of single column RCE picture. And in fact, I think that's right. This 2013 paper by Mariner et al. Used a very simple single column model, which was just a model of, it had a moist adiabat, and it pegged the column to 80% relative humidity. And what they found was an ECS bump. So this really is just a fundamental aspect of something going on with radiation, maybe water vapor, almost certainly the moist adiabat, the temperature structure of the column. So how does that then relate to what's going on in the GCMs? And I don't have the answer to that, but what I can do is collect some of the results that are in the literature. So that's what I've attempted to do here, is to take different simulations from different papers and put them all in a common footing to see if there are consistent behaviors. Because some papers report a bump, some don't, but are they probing the same temperatures? So this is a way to get at that. If we look at forcing, we see that forcing increases monotonically in all the simulations that I have data on here. So that's nice to see consistency there. If we look at -1 over the feedback parameter, or what some people call the climate sensitivity, we see a bump. We see a spike there. My cloud resolving simulation is the brown dot dash curve at the bottom. Its bump is much less than what you see in the GCMs. Again, something we need to understand. Why is there that difference? If you multiply this together, you get the ECS. And only 4 of the simulations have probed the ECS bump, to the best of my knowledge. And one of them is my cloud resolving model. The other is that very simple RCE model, the moist adiabat model. And then 2 are GCMs with the higher ECS bumps. So this is something I think we really need to understand better. And but to do that, I think we should be running GCMs, and we should be probing at very fine temperature intervals. And so a proposal that I have at the very end of this paper is the very last paragraph. If you want, you can skip the whole paper, go to the last paragraph, and it's a proposal for how to speed up these equilibrations in a global climate model. I'm not sure it works. I haven't tried it, but I think it's promising, and it might be a way for us to get at this problem and really understand what this ECS bump looks like in a variety of different models. Again, we have the ability, unfortunately, to push our climate back to an Eocene-like state. And so we should understand what waits for us there in that Eocene-like state. Is there a cliff that we can fall off or not? So I'll end there. Thanks.